My name is Charlie Payne. I'm pleased to introduce the next speakers, which will be on our program, an ACVIP Overview. This is our 10 o'clock session, starting just a couple of minutes early. Let me introduce our speakers. Alex Boydston is electronic engineer for the US Army's Development Command at Aviation and Missile Center at the Technology Development Directorate for Aviation at Redstone Arsenal in Alabama. And he was the project lead for ACVIP development under the Joint Multi-Role Science and Technology Program. He's now working to transition these technologies to other Army programs. Following Alex will be Sholom Cohen, who's a principal engineer with the Software Engineering Institute at Carnegie Mellon University in Pittsburgh, Pennsylvania, where he leads ACVIP and AADL investigations. And then Tyler Smith, a software engineer with the Adventium Labs in Minneapolis, Minnesota, where he leads ACVIP and AADL investigations there. They will present an overview of the architecture-centric virtual integration process and its engineering assets. If you have any questions, please add them to the Q&A, and I will bring them to the attention of the speakers at the appropriate time. Alex, please feel free to go ahead.
Okay, welcome everyone again for the next briefing. Can everyone see my brief? I'd like to get an acknowledgement on that.
I can see it, Alex.
Okay, fantastic. All right, we are going to give you an overview of ACVIP before we head into the more specific tools that other people and their experiences that they've had with ACVIP and AADL. I have been working ACVIP and AADL since 2013 on the Joint Multi-Role program, where we did more than just ACVIP and AADL. We had to prove out various concepts such as the Joint Common Architecture and FACE and HOST, those things that we were talking about in Scott's briefing. I really appreciate Scott's overview from his perspective as a chief architect over in the MOSA Transformation Office. But today's briefing that I'm giving you is called Architecture-Centric Virtual Integration Process Overview. Myself, Sholom Cohen, and Tyler Smith will be presenting this. So we've teamed together on that. All right, so I'll start out with the overview and background, and then Sholom will give the acquisition management guidance, and he'll cover and touch on the open source AADL tool environment, or OSATE, and then Tyler will close with ACVIP modeling and analysis and the CAMET tools, or curated access to model-based engineering tools. Okay, so as an overview, some of you probably have heard this before, but the core aspect of ACVIP is to identify issues early in embedded computing systems. ACVIP really focuses on the embedded computing software intensive aspect of a system. So you may wonder, in the context of big systems engineering, there is a language of Sysml, which models the larger system engineering requirements from a conceptual, functional, logical, physical aspect, but ACVIP really drills into the embedded systems aspect for the avionics and software that would be in a system, or even on a shipboard or other systems, anything that deals with embedded computing systems. We apply ACVIP during the development and sustainment to try to reduce risk before we get into the actual integration of these systems. We see over and over challenges in that area. And it deals with modeling and analyzing aspects such as timing, safety, cybersecurity, those things that are critical for those types of systems. ACVIP provides a virtual integration environment. We're going to talk more about that, and you'll see examples of tools in the other briefings that are coming down the pipe. But it is doing virtual integration, trying to identify defects in a manner where you've modeled that, and trying to represent the system to think through and identify where there might be mistakes in interfacing or the timing may be wrongly specified, to identify those issues. And we have capabilities, analysis tools that goes along with the Aadl model to help identify those things. And as Scott was mentioning, and we were talking about, this whole process of ACVIP is supportive of DevSecOps. There is a mechanism for continuous virtual integration. Adventium did a pilot program before the capstone demonstration and proved out a continuous virtual integration toolkit where it was pretty much a agile and DevSecOps approach there. It provides a consistent representation for an embedded system. All the properties that are in Aadl represents things such as processes, processors, memory, data buses, those types of things, threads. So it's at that level that you can represent a system and get into the hairy details of an embedded computing system and the network of that system. So, and the Aadl is supportive of that. So we've seen, as I said before, and you've identified before on major ACAP-1 programs where we've had challenges. I hate to beat up on the F-35 program, but we know that they've had challenges. They've had their own challenges with various things, not just in computing, but a large part of it has been in software rework. And we saw last year a GAO report that came out with regards to that and identified issues with metrics and those sorts of things. But had the F-35 program done more of this type of modeling analysis, we pretend that that they would have had less problems on that. I won't say that that would eradicate everything, all the problems that they've had, but it would help ameliorate those issues. So you can look up the GAO report there that's identified on that chart. Here we see this depiction that several of you probably seen before. Again, the whole aspect here is the faults are introduced early. It's during the requirements and the design and development that those faults are identified, and we don't find much of those because quite honestly, we wait until we get to test phase to identify those things. And it's at that point that we identify that, hey, we've got an integration issue here. Our timing's off, the protocol doesn't match up, the messaging doesn't match up. We got to go change things. So sometimes that requires a requirement change, and those things are very expensive to deal with. So if you can do anything to ameliorate, to reduce the effect there, to mitigate the problem, well, then you've bought yourself something. I think that there was a study that was done by the Air Vehicle Systems Institute, where basically they said that if you can identify 10% of the problems, that you would pay for a process such as this for virtual integration. So that's what we want to target. We want to try to save money because we have less of that these days. And then here's another depiction where ACVIP increases design confidence, basically, again, starting as early as the requirements and functional architecture development, and then the definition of that system architecture, and then flowing into the, should say, hardware and software architecture before you do the integration of the embedded system here. Our point here is to detect the integration flaws before they become a problem. And as the design fidelity increases, you're going to increase your confidence. So that's the message there. And so what have we done for ACVIP? Scott had mentioned it, that we've done a lot of work in S&T over the past 7 years or 8 years. We had a program called the Joint Multi-Row Program to prepare future vertical lift. And as I said, there was a lot more things that were going on than ACVIP, but we had elements of that. Our very first demonstration was the Joint Common Architecture demo, and we had an ACVIP shadow where the SEI and Adventium participated in doing requirements analysis, safety analysis, and timing analysis. We found over 80 issues in that particular demonstration before the actual integration occurred. And we had 2 TIA partners, Boeing Sikorsky team and Honeywell team, to create a data correlation fusion manager that was integrated into a system that the Army had. And we did that virtual integration of that before the actual integration occurred. And then the second demonstration that occurred on Joint Multi-Row was the architecture implementation process demonstrations. We had 6 different TIA partners or technology interface agreements integration agreements where we were working with Boeing, Sikorsky, GE Aviation, Honeywell, Lockheed, Northrop Grumman, and at the time it was called Rockwell Collins. Now they're Collins Aerospace. But we gave the tools, and they conducted their own modeling and analysis and exchange of models. And that was a very, very revealing activity demonstration. We learned a lot about our tools and the things that needed to be improved on that. We worked on the improvement of the tools in preparation for our final demonstration, which was the capstone demonstration, where we had these particular participants. We had an architect with Scale Harris, and we had 3 MSIs, Collins and Raytheon, and Boeing Sikorsky. And I think that, yes, this chart here has an error in it. I'm missing Honeywell as basically the JCA product developer. They were the software developer. So the software developer provided their components. There were several components that were provided and that the mission system integrators needed to integrate into their system. The mission system integrators also had their components, and ACVIP modeling and analysis occurred on that. So there were some findings out of this. As I said, JCA demo, we found over 80 issues for integration. The AIPD, one of the significant things was by doing model-based engineering in general, model-based systems engineering in ACVIP, that basically you could have a 10% gain there where you could reduce cost and reduce rework on that activity. And then Sholom Cohen's going to go over what one of the findings was out of the capstone demonstration from the MSI, where a reduction of 30% was identified there. So we've done a lot of work in the maturation for ACVIP and AADL, and we believe it's proven and ready for transferring over into the program of record, and we are applying that. So we've conducted that exercise that I just mentioned on our 6.3 S&T program called Joint Multi-Row, that we had evidence, as I had mentioned there, of identifying the issues, reducing the overall cost in an effort there by doing some 3 times upfront effort, because you got to do the modeling analysis, and reducing the issues by 10 times on the back end, and then a 30% reduction on the capstone demonstration. And then we also demonstrated the ability to do continuous virtual integration with that pilot program that Adventium showed, and showing that ACVIP can be supportive of Agile. And then all of this wrapped into the Sysml and AADL having the authoritative source of truth there support. So with all of that, we pulled that together, the elements of the handbooks for ACVIP, and the capabilities to do the translation that Scott was mentioning for Sysml to AADL, FACE to AADL. All that guidance there is now contained in what we call the Future Vertical Lift Architecture Framework, or FAF. And the requirements for ACVIP are contained in FAF. And we are using it on our programs for FARA and FLARA in our GFI models, which also has not just FAF, but has the system performance specifications. And we have echoed requirements in our statement of work and our systems engineering plans. So ACVIP is transitioning from S&T work, from 6.3 S&T work, over into the program of record. So that is my last chart. I will turn it over to Sholom Cohen, and we will be gathering your questions as we continue. Sholom.
Thanks, Alex. Getting feedback here. I think I'm okay now. Good. So today I'm going to be talking to you and building on some of the conversations we just had between Anita, Scott Dennis, and Alex to talk about where we're going with ACVIP, with OSATE, and how we look in that direction to improve the overall ability of the government to acquire software and to develop it successfully in field software systems. Can we go to the next slide, Alex? Thank you. One more. Okay. Anita mentioned in her talk the fact that the first ADL user day was in 2019, and almost coincident with that, within a few weeks of that, we had a visit from one of the FVL program managers, namely Dan Bailey. And he came to the SEI with a basic question, which was, how do I get ACVIP onto contract for FARA and FLARA, the FVL systems? And one of the responses to that was, well, we need to get the proper contract language in place so that you can require the use of these tools, techniques, and so on in an acquisition. And we did do that. Alex mentioned the FVL architecture framework, FAF, and the contract language is present in that architecture framework along with various other requirements for ACVIP. But we also determined that really a specific set of contract language was not sufficient. We couldn't just direct the contractors to apply a technology without that technology being sufficiently mature with training, tools, techniques, guidebooks, and so on in order for them to use it successfully. So as Anita mentioned, we spent really the last 3 years addressing those transition issues. Some of them came out of the Capstone project that Alex referred to. Some of them come as a result of our interaction with the actual FVL performers to be able to improve the ability of the government to require the use of ACVIP during contractual acquisition and to be able to make it a success story for all those involved. So specifically, the response to Dan Bailey came about in a couple of different areas. We developed and matured tools and techniques, and we'll say a little bit about OSATE in that regard, as well as the tools that Adventium has developed. Tyler will be going through the tooling that has been developed on the Adventium side that's usable within the OSATE environment. We also did an extensive look at the MBSE frameworks, the digital engineering concepts, the processes and templates that are part of FAF to determine where ACVIP could be used and could be applied to improve that process. One of the concepts that Anita mentioned briefly or in passing was this idea of moving left. And I think that Alex highlighted that in his chart to say, well, we know that a huge volume of defects is introduced very early in a program. We look at the development timelines moving from left to right. On that left side, we do specification, we use some early architecture and design work. And quite often, defects are introduced there that aren't realized and can't be addressed until late in the development, implementation, and sometimes even in operation. So the goal here is to introduce ACVIP into MBSE early in the development process to be able to identify those. And I'll say a little bit more as I go through this presentation. We also worked with a variety of contractors, including SBIR work that will be highlighted later on in the program from IDT, where we did extensive work with them, integrating MBSE tools with ACVIP and ADL to be able to test and verify the virtual integration along with actual implementation results. And finally, we went about transitioning the documentation, models, and tools through work with a variety of ADL users. Some of those are included in on the program today. Those that worked on the Capstone and the other mission system architecture demonstration projects. Some of them are in academia, where we have an ongoing activity to support programs that are using ADL, and as well as with commercial developers who are really not part of the necessarily part of the DoD framework, but who are using ADL in some of their ongoing project developments. So those are all kind of exciting areas of work and evolution of the products. And we're trying to include and integrate the results of those into the future to make ADL and ACVIP usable and transition to the Army in particular. So Alex, if you go to the next chart, what I show here is a diagram that we use in the AEDL and ACVIP Acquisition handbook. This is a handbook that was developed initially for one of the early MSTED projects, and then as an output of Capstone, we did major revisions so that we could address that question of Dan Bailey, transitioning ACVIP into the community of the FEL project. So we now have a mature acquisition handbook, and early in that handbook, you'll see what I call the 30,000-foot view of ACVIP. At the core of this diagram is some of the technology development, maturation, research activity to understand what MBSE needs. Scott Dennis mentioned that MBSE and Sysml carry us to a certain point, but we need some additional support, particularly in the area of modeling with analysis, not just modeling to produce diagrams that we can review and develop shared understanding of the intent behind the model, but also build in analysis to the models as soon as those are sort of in parallel to the development of those models. So that type of work is at the core of our activities here within the SEI and within Adventium as well, in support of Army and ongoing projects. But if you look at the top, you'll see what we typically see as acquisition programs, developing specifications and providing those specifications as government furnished information to a collection of contractors for their development. And as you proceed around around this chart, you'll see the specific activities of refining requirements, understanding those, improving them, moving from requirements to architecture to design, implementation, and so on. The idea of a circle is really that DevOps perspective, that as a product is under development, it never really stops being under development. You may say, well, it reaches a certain release, but then that release is followed by improvements, extensions, new elements, integration or interoperation with other systems that are related to it, and some that may not have been anticipated for those kinds of interoperability activities. So there's a constant flow of requirements that are evolved even as the product is under development. And we hope to capture those, or want to capture those in ACVIP so that we can do this analysis. So when we think about moving to the left, if you take a linear view, if you take this cyclical view, then you're kind of moving counterclockwise. The diagram there shows a clockwise movement, but moving back, we don't want to wait until the system is in the field to perform the final validation. We want to be able to validate requirement statements as early as possible in the development. And we've done work through several scenarios where we take a specification statement from system performance specification and ask questions about that statement. What is the connection? What are the connections between this requirement and another requirement? Is there a data flow implication? Is there a timing or a data volume? Are there bandwidth issues that will arise as a result of this performance statement? And we can model those in ADL as early as the specification time to ask these questions and to understand whether the requirement itself is correct, is it complete, are there any ambiguities, is it verifiable, is it analyzable? Those sorts of questions come up early and can help us identify potential defects before they haunt us at the end of a software development. They don't take a lot of effort. We're not doing a highly refined, high degree of precision on the analysis. We're more looking to see, is the requirement analyzable? And as opposed to an approach where a contractor takes a statement and derives other statements from it, maybe provides or inputs their own interpretation, or says, well, I've got a legacy that can handle this. and somewhere downstream towards the end of the integration, that a problem occurs and it's discovered that there was a wrong assumption that was made. We want to avoid those types of assumptions and make sure that the issues and questions come up as early as possible. So do you want to go to the next chart, Alex? We see the improvements or the potential for improvements on this particular chart. Now, this is developed by one of the MSAT performers. It's based on some collection of actual results that they accumulated during the course of the MSAT capstone development, which was a full up development of a mission system. But in addition, they looked at a couple of specific factors to try to estimate what was the overall impact of using ACVIP during this development. Some of the numbers are actual results. Some of them are based on extrapolating for those actual results to give a more comprehensive picture of the impact of ACVIP. So if you look at the left side, again, this idea of moving to the left, if you look at the left side, you'll see across these three lines, three different levels of effort. There's one that's highlighted in red, which is the estimated effort without ACVIP. This is kind of a hard number to come at, but it would be sort of if we did not have ACVIP, if we're trying to develop software, perhaps using MBSE, but in the, let's say, traditional way of developing software, what would the effort be at each of these different phases of a development? And you'll see the chart as you move to the right, increasing and becoming significant in the end state, where there's a lot of integration, test, build, fix kinds of activity that go on when there are assumptions, let's say, introduced early that then have to be corrected because defects were introduced early in the process. So that red line shows what would happen if we didn't use ACVIP at all in a project. The black line, the top line, was actually the measured result. This was the actual effort that was expended at each of these phases. And of course, there was savings, as it's shown here, towards the end that were realized because of the use of ACVIP. ACVIP reduced some of the defects and eliminated the need for some of the test, build, fix kind of activity. The virtual integration uncovered problems, and they did not have to be addressed late in the implementation. But there was a third line that the contractor developed, which is the green line. And that was an estimate to say, well, what would happen if we had gone full out and applied ACVIP as effectively as possible as early in the process? And one of the things you'll see right away is this move to the left. There's quite a bit more modeling activity on the left side of this picture than in either of the two other lines that are shown there, the one without ACVIP or the one with the standard MBC development approach. The modeling activity, certainly the level of activity at the level of effort increases by a substantial margin, but the result on the right end, as the program is finally integrated and released, shows significant savings of about 30%. And that's the number that we're looking for. So on the right-hand side, on the left-hand side, you'll see greater investment in modeling with analysis according to the ACVIP principles. And as I said before, part of the effort was to improve and mature the tools so that that becomes a more natural way of developing and testing and analyzing the early architecture and design phase models. And then towards the latter part of the development on the right-hand side, you recognize or realize those savings plus more in reducing the overall implementation test and the fact that there are not as many defects discovered late in the process, a much more efficient drive to the final release of the product. Okay, don't see any questions yet, so we'll go to the next slide, thanks. Now, we talked about some of the investment in research, development, and so on, so that's continuing on to this day. And as as we speak right now, we're seeing a significant effort on our part, both from the Army as the integrator of ACVIP related technology, as well as from the SCI and from Adventium, working with programs of record, the programs of record in particular for FEL, to integrate ACVIP into the acquisition and into the implementation and development activities that those FEL performers are actually engaged in. So that's a major effort that we've undertaken. And in addition to working specifically with the programs, we're also working with some of these broader initiatives. And Scott Dennis highlighted that in particular in his talk in regard to MOSA, in regard to DevOps, Agile development, and so on. These are areas that we have certainly engaged in the past, but are becoming a significant part of the effort as we move forward. We're integrating with these large-scale acquisition programs of record and recognizing that the first step in getting ACVIP as part of their acquisition process is to have a plan for applying ACVIP. Part of the ACVIP acquisition handbook includes an ACVIP plan or a template for an ACVIP plan that's tailorable to the individual project. And we're working right now on a specific ACVIP plan for one of these programs that involves looking at the kinds of scenarios, the kinds of activities that in the past have proven to be difficult, and making sure that the ACVIP approach is applied successfully to address these kinds of acquisition scenarios. And if ACVIP doesn't apply, to come up with other approaches that can address those gaps, and to recognize that MBSE is broader than ACVIP, but ACVIP should be effective in addressing some of the gaps that we currently recognize in the MBSE approach or most of some of these other initiatives. We're also looking at ways that ACVIP can be applied using what we're calling here new and emerging workflows. It's in integrating ADL, OSATE, the related OSATE analysis techniques, but also to transition into other languages or to other tool support that can improve the overall process for MBSE in areas where ADL is not currently applied, but may be applied in the future. So how do we transition from Sysml, the current Sysml, or the new anticipated release of Sysml 2? How do we improve the ability of those modeling languages to work concurrently with AEDL to improve the analyzability and the release of products that are virtually integrated and are correct on delivery and in the initial, let's say, airworthiness testing of those products. We're also applying modeling with analysis to product line development in the area of systematic reuse. And I've tried to emphasize the term modeling with analysis. Scott mentioned that, well, Sysml gives you a rich set of diagrams that are used in reviews and used to accomplish common understanding, but we also want to do modeling with analysis, and the ADL and ACVIP feature that particular aspect. Here we're applying it to product lines, to systematic reuse, and we're working with one of the Army S&T projects to release a strategy for developing product lines of components to satisfy system needs, as well as governance and modeling approaches to develop those components and use them in projects. Finally, OSATE as a tool has been out for probably about 10 years. Scott Dennis mentioned some of its predecessor tools, but OSATE now is in a release 2 based on the AEDL standard. It is AEDL 2. We recently saw the publication of updated standard, and we're upgrading OSATE to cover the features of that improved standard, new release of the standard, and it's still AEDL 2. Over the course of the capstone effort, we saw vast improvement in the graphics that AEDL can be applied to, and in the OSATE to support the development of graphics to illustrate what's present in the AEDL textual language. Some developers like to go from text and then project that text into a graphic. Some developers like to start in the graphics and then move directly from the graphical depiction into the analysis. And the graphical editor allows someone to work in either direction or start with text, move to graphics, make changes in the graphics, and have those reflected back in the text. So that was one of the major improvements. And there are other areas, particularly for transition, in terms of training, examples, webinars. Both the SEI and Adventium have stand-up classroom training, as well as online training support and examples to help with the transition of the tools and the techniques to new users. So finally, on the last slide, I'm going to go to the last slide, Alex. Give some guidance for all of the audience out there who are interested in joining with the SEI, Adventium, and the Army in this direction of improved technology and adopting the technology that's there. In particular, on the SEI side, we have support for the technology with publications about ACVIP, and some of these are technical reports. Some of them are some of the research work that we're doing that's semi-independent of this activity. It's looking at future developments. Some of them are DevOps. Some of them are improvements in analyzability. Some of the improvements in certification issues, and the case and analysis for provability of correctness of designs and architecture. We're also improving the ACVIP plan and some of the deliverables that a project may have to make sure that we're addressing those needs in terms of, as I mentioned just now, assurance cases and other areas where we want to make sure that not only can we develop and document the software, but the development and documentation leads to successful airworthiness certification and release of products. In terms of using our technology, we've been very active in maintaining and improving the ability of the tools to be usable in the community. They're open source tools. These are examples. There are case studies for the development. The OSATE base tool is available free for use. And then there are examples of various other resources that are available to any organization who would like to begin to experiment or to delve into some of the deeper areas of applying this technology. And as I mentioned, there's a wealth of introductory webinars and other kinds of resources that you can avail yourself of for training. The digital engineering transformation offers an obvious target for this work. And so we're working actively with those organizations within the Army, within the Air Force, and other organizations to determine how to integrate these ideas into the digital engineering transformation. And I finally list a contact there if anyone wants to follow up. Well, that concludes my portion of this panel session. I don't see any questions on my board. So I'll turn over the panel now to Tyler Smith for the discussion of the Adventium activities.
Thank you, Sholom. Good morning. It is not showing me my video. Is my video showing up? It's not giving me a preview of.
Yes, it is.
All right, cool. Well, good morning, everybody. Thank you for taking time to join us today. I really appreciate it. Before I get started, as we were listening to the comments from Scott Dennis and Alex and Sholom, I was just reflecting on it. It has been, at least for me, just about 8 years of working with OSATE, Aadl, and ACVIP. And it's been just a blast getting to know everybody that you're seeing present today, and really moving from just being colleagues and coworkers to developing friendships with folks as this work has progressed. And so I'd like to publicly acknowledge, especially with folks like Alex and Sholom, who I've worked with for the entire 8 years. It's been a lot of fun, and I really have enjoyed getting to do this work with you all. So with that said, let's get started with my portion of the presentation. Again, my name is Tyler Smith. I am a research scientist at Adventium Labs. And what we're going to be talking about today is kind of the next step in the logical progression of what you've heard from all of our presenters. Scott Dennis gave us the foundational concepts of MOSA and the analysis and shifting left to analyze components, specifications, key interfaces. Then Alex built on that with the overall ACVIP philosophy for the analysis of embedded computing systems. And Sholom built one step more on top of that, talking about OSATE and the phenomenal foundation for research that the SEI has provided. There are tons of research projects all over building on the foundation of OSATE. And the SEI is providing that. And that's awesome because companies like Adventium or IDT are able to start from that and build. We don't have to start from scratch. So what I'm talking about today is a product of Adventium's called the CAMET Base Pack, which is 5 tools for virtual integration and analysis with AADL. Again, these tools build on the prior work that's been done by the phenomenal folks at the SEI. So the CAMET Base Pack, Anita mentioned there's advanced analysis capabilities that OSATE enables. CAMET Base Pack is a collection of those capabilities. In this talk, what I'm going to do, whoa, too far. In this talk, I'm going to briefly summarize all of them on this slide. We'll talk through details of each of the tools, and then we'll recap and wrap up. So CAMET Base Pack is a collection of advanced analysis tools. These are some of Adventium's tools that are the most robust, mature, and popular. We decided to put them together so that if you're new to this AADL modeling and analysis and you're starting to dip a toe into some of the advanced analysis capabilities, this is an easy, straightforward place to start. The CAMET Base Pack provides for timing and schedule analysis. It provides for domain separation analysis. It provides for security isolation analysis and supports the use of the risk management framework. And finally, the CAMET Base Pack provides the Sysml to AADL translation capability that Anita mentioned in her talk earlier. So using all these pieces together, you can incorporate AADL and ACVIP into a larger engineering workflow. And you can, as all of the presenters have said so far, and I'm sure all of them will after me, move left in your system engineering to find defects sooner. Next slide, please. So first up is the Sysml to AADL bridge. This is, we were a little bit caught off guard on how popular this tool is. And in retrospect, it kind of makes sense because huge number of people use Sysml. A lot of people were interested in AADL and the robust engineering analysis capabilities of AADL, but it's a significant leap to learn an entire separate language. The Sysml to AADL bridge makes that a much smoother transition. Well, I mean, it's a bridge. You no longer have to make a leap. You can just walk across. What it does is it provides a Sysml profile for use either in Cameo, Magic Draw, or Sparks Enterprise Architect that allows you to annotate your Sysml model with AADL stereotypes, then with a single button click, generate an AADL model that you can analyze. Now what we're seeing on this slide is a graphical AADL model. You might remember from Shalom's talk a moment ago, there's been a ton of work by the SEI in the AADL graphical modeling capabilities. This is a really cool example because without having to write any AADL text, I can take a Sysml model, annotate it, generate AADL, and then use OSATE's AADL diagram generation tool to generate this graphical representation that you're seeing in the bottom right-hand corner of the screen. That is super cool. And it works really well, and it works fast, and it works cleanly. And I'm really excited about it, and it's fun to show it off. Next slide, please. All right, now we're on the first of the 4 analysis tools that I'm going to talk about today. This is the Faststar timing analysis and schedule generation tool. There's a lot going on here, so let's break this slide down piece by piece. On the upper left-hand corner, what we're looking at is a architecture that shows the 2, I think of them as levels of representation that AADL provides. AADL lets us represent software and semantic connections shown at the top of the upper left diagram between 2 software threads. And in AADL, we use this term binding. When we have software and semantic connections, we bind those to hardware to show that this is the hardware that is actually running the software. That's a really important piece of what AADL provides. The Faststar timing and analysis tool looks at both the software you've defined and the timing properties of that software and the platform that provides the infrastructure to run that software. It analyzes all of that together to give you information about flow latencies, about thread deadlines, and it can even use that to generate an ARINC 653 partition schedule for you. If you've ever tried to do a 75 partition schedule by hand, you know how helpful it can be to have something generate that for you. Next slide, please. All right. Next analysis tool we're going to talk about is the multiple independent levels of security, or MILS tool. For those of you not familiar, MILS is an industry standard practice for ensuring separation for confidentiality, meaning we want to keep different labels or different types of information separate from one another. What we're showing on the left-hand side of the screen right now is a software architecture specified in AADL, and we've taken security labels from the environment that this software is running in. So think of your secret, top secret, or coalition as different types of labels you want to apply, and we propagate those security labels through our architecture. Then we specify where in our architecture we need to have a cross-domain solution. For anyone not familiar, a cross-domain solution is a certified and approved component that is allowed to touch multiple security domains. So if you're going to let information flow between a coalition and a secret network, for example, you need a certified cross-domain solution in the middle to make sure that only approved data can go across that connection. What the MILS tool does is it looks at your architecture and it looks at the connections and the bindings. Remember that word bindings from the Faststar slide. It looks at the connections and the bindings in your architecture to determine that whether you have cross-domain solutions in every place necessary. And it will flag for you any places where connections or bindings exist between differently labeled pieces of your architecture. So as we get more and more involved in coalition activities, where it's not just US forces alone, but it's US and coalition forces, it's increasingly important that our systems are able to deal with multiple levels of security. And we want to be able to have architectures that support that without having to add lots of overhead in terms of additional hardware components. By being able to analyze software and hardware separation in a rigorous fashion with AADL and ACVIP, we can increase confidence that we'll have a correct architecture and that we won't have to go back and rework our architecture after we've assembled the entire design. Next slide, please. Okay. Next up is the risk management framework. Just like MILS, RMF is an industry standard specified by the NIST publication 837. RMF describes a process shown here on the left-hand side of the screen, for categorizing information in your information system and applying and implementing controls on that information and on the system that will process that information. So with the MILS tool, we were looking at, does your architecture correctly isolate different security labels? With RMF, we are providing a capability to label your information, as shown in the bubble for step 1, where we apply confidentiality, integrity, and availability labels to data. Then we determine which security controls are necessary, and we apply this information to our AADL model, and the risk management framework analysis tool determines whether you have appropriately allocated your labels and requirements to your architecture. Next slide, please, Alex. So this analysis tool does 4 different things for us. First, if we have multiple flows, when I say flow, I'm referring to an AADL data flow or end-to-end flow. First, the RMF analysis tool checks if one flow can interfere with another. Next, Alex. Next, it checks whether a flow that's bound to hardware, what you're seeing here is the data flow is the arrow on the top, and the 3-dimensional blocks are the hardware that it's bound to. Again, there's that word again, binding, meaning we've got some software that is running on hardware, it's bound to that hardware. Does the hardware have the appropriate security controls applied to it? The tool checks for non-bypassability, meaning is there any way for this data to get routed around the security controls? And finally, it checks for tamper resistance, meaning is there anything that would allow somebody to manipulate the security controls applied to hardware to which a data flow is bound. So again, altogether, the RMF analysis tool is an aid to help reduce the risk that your architecture will fail a security assessment. It helps you apply the RMF process. Next slide, please, Alex. And sorry, I've got a timer going and I'm making sure my phone stays awake, so I'm staying on track. All right, and the last tool for today is the MADS tool. So remember from several minutes ago, we talked about the MILS tool, the multiple independent levels of security tool. The MILS tool is reasoning about confidentiality. Are we keeping data isolated appropriately according to its labels? The MADS tool is a more generalized tool for reasoning about data or domain separation for different kinds of domains. So we could reason about safety separation. Are we appropriately keeping high criticality data separate from low criticality data? We want to do that because we want to ensure that our architecture appropriately isolates different components that are required to perform different levels of capability according to what we need them to do. What we're showing on this slide is an example of if we want to monitor or we want to assess our architecture for integrity loss, if we're concerned about integrity of data as it progresses from a sensor on the left to a flight planner to controls to a control surface, we want to maintain integrity of that data. We don't want data to get lost, or we don't want packets dropped. We don't want data to fall through the cracks. What that means is if we're talking about the domain of criticality, we apply a label of this is critical data. We need to maintain integrity of this data. Everything in this data flow, every piece to which this data flow is bound, the sensor, flight planner, flight controls, has to provide that level of integrity. We apply a label to it and we assess, does every piece in this flow have the appropriate label? Now highlighted here is this yellow piece, logging. If I'm assembling an architecture and I decide to put my logger in the critical flow path between flight controls and control surfaces, what MADS is going to highlight for me is it's going to say, whoa, slow down. You've put a piece of software or a piece of hardware in this path, but it's not labeled with the same level of criticality. In the domain of criticality, it is got a different label applied to it, and it is not appropriate. You've broken the chain. You have mixed your criticalities, and we no longer have an appropriate architecture. MADS highlights this type of situation for you so that you can determine either A, if logging really does need to be here, I need to change my requirements for my logging system so that it provides better protections against integrity loss, or B, I need to change this data flow so that logging is no longer in the path, so that a loss of data that occurs in the logging infrastructure doesn't disrupt my critical data. So that covers all of the tools in the CAMET base pack. I'm going to really quick just verbally state them again, and then we will open it up for questions. Alex, I think this is just backup charts right now. So you can just leave it as, yeah, acronyms is good. We have a lot of acronyms. So just to recap where we're at, since I think I have about a minute left. We started saying we've got this MOSA approach that Scott Dennis identified. Anita, Alex, and Sholom talked about infrastructure that's been built up through years of investment by the Army, SEI, and others to provide a foundation for advanced analysis. I talked through several advanced analysis capabilities provided by Adventium's CAMET base pack of tools. Then through the rest of the day today, you'll hear about additional tools, capabilities, and use of those tools by other ACVIP performers and stakeholders. So with all that covered, thank you all very much for your attention. Thank you for your time. And we got a few questions here. Oh my goodness, we have.
Tyler, let me direct the questions. I guess that we have about 5 questions that have been posed during your talk. First question's from Brian Larson, and Brian, I'll pose this question to either of the 3 of you. There are 2 questions that Brian asked. Does provability of correctness require formalization of behavior specification and implementation? And how do you demonstrate that you've conformed the implementation to the architecture? And that might be a Sholom or a Tyler question of this.
Sure, I can take a quick attempt at that answer, though that is a heck of a question for a short answer. So I'll give it a shot, and we can certainly dive in further. The short answer is provability of correctness is extremely difficult. And I hesitate to say anything can be broadly proven correct. Before you can prove anything, you have to state assumptions and define the narrow scope in which you're going to prove anything. To give a specific example, if we're looking at the Mills tool, we make assumptions. For example, the way the Mills tool works, it operates on an AADL model. And so it's not reasoning about physical model, it's reasoning about the AADL model. If we assume just talking about AADL model, and we assume that the AADL model is correct and it semantically follows the AADL standard, then we can make some assessments about the behavior of the system. So in short, my answer is yes, you need to have a formally correct specification because you can't reason about anything without making some assumptions about words you're using and the language you're writing things down in.
Great. So do you would agree that it requires some formalization of behavior specification as well? I think that was his key question. Sure.
I think broadly, yes, but I would caveat my answer with it really depends on what specifically you are trying to prove. The amount of information and the type of formalization depends on what you want to learn or what you want to prove.
Sholom, do you want to say anything more about how conformance of the architecture to the implementation is enforced, is achieved?
I won't go into the detail. I think there's quite a bit to add to that, but we do have a research project currently underway that is looking exactly in that area. And that's called Enabling Transition of Model-Based Engineering Using Assurance Contracts. I mentioned before this idea of assurance cases. What information do you need in order to make sure, provably is maybe too strong a word right now, but it's raising the level of assurance that the model reflects reality and that the results of the analysis can be carried forward into implementation with a high level of confidence. And so this research effort on engineering for assurance contracts is the primary focus within the SAI of addressing this question. Whether it's formal analysis or not, or formal provability, that will probably be something that we're looking at over the next couple of years.
Another question for you, Sholom. Sablu asked, is there a direct translation from UAF to AADL?
Actually, I think that's probably more for Adventium. The Sysml profiles could be applied, I guess, to some of the UAF constructs, some of the views, and there are certainly parallels between block diagrams and some of the UAF views, but I don't want to speak for Adventium, but I don't think that right now you're looking at UAF itself. We are, on the other hand, looking at FACE, and the FACE, specifically the FACE data modeling language, and do have a translator that goes directly from FACE model integration, UOP, and data models into an AEDL representation that can then be enhanced for analysis. But I'll turn over to Tyler for the UAF question.
Sure, good question. So as far as a direct translation, I'm not sure exactly what you would mean by direct translation, because I don't think UAF and AADL really are kind of analogs to one another. However, I'm not aware of anything that would make them conflict, because AADL, to do the translation from Sysml to AADL just requires use of AADL stereotypes in regular Sysml. So I don't think there's any barriers to applying AADL stereotypes to a UAF Sysml model.
Great. I've got another question from Scott Kinney, and I think this has to do with some of the analysis tools. Is it possible to generate 802.1q TSN scheduling?
Sure. So the analysis tools today, by my best recollection, do not support TSN scheduling. The tools I discussed support ARINC 653 processor partition scheduling. However, Adventium has done some previous work on schedule generation for networking in particular. It's been long enough that I cannot remember the specifics of that. So Scott Kenny, I'm not sure if I have your contact information, but I'd be happy to take an action to follow up with you on that later, if that's something you're curious to learn more about. I'm not sure if you can send me a direct message or not, but we'll figure it out.
Scott, just send me an email on that and I'll get an answer back to you from Tyler.
Thank you, Tyler and Alex. Final question that we have in the Q&A window, and if you have any other questions, please feel free to post them there. From Bill Richardson, how do the ADL bindings how are they represented in Sysml? And I'm thinking this is probably a Sysml ADL profile question.
Yep. So the AADL bindings are specified using a Sysml allocation relationship, and then you apply an AADL binding stereotype to the allocation relationship. So if I was going to bind a software process to a hardware processor, I would create a block for the process, block for the processor, apply the AADL process stereotype To the process, apply the Aadl processor stereotype to the processor, create a Sysml allocation relationship between them, and then apply the binding stereotype to that allocation relationship.
Thank you. I don't see any further questions, but if you do have some, please post them in there, or you can reach out to the participants directly. As you probably saw from our tech support, our organizers, the break has been moved from 11 to 11:15. So we will take a short break here as planned. We'll just shift every session will get shifted back about 15 minutes. So plan that accordingly for the rest of your day. If I see no other questions, I think we will go ahead and take our break. And thank you very much, Alex and Sholom and Tyler, for your great presentation.
Thank you very much for your role as MC, Charlie. Much appreciated.
Yep. Thanks a lot, Charlie.
You're welcome.